Hello, I'm Averill. I'm the state soil scientist with the USDA's Natural Resources Conservation Service. The Natural Resources Conservation Service, or NRCS, is the federal agency responsible for helping landowners prevent soil erosion and improve water quality through various conservation practices. We provide conservation technical assistance, predominantly to farmers, but others as well. And in so doing, we are also responsible for the inventory of the nation's soil resources. And that's what I've personally been involved with for my career, and that is to make soil maps and gather information about the soil maps and provide interpretive information so that people can make wiser land use decisions. We're here today to help folks who are working towards preparing for the Massachusetts Envirothon. I've been fortunate to be the soil station coordinator, and I'm the person who has put together the exam for Envirothon students to take during the day of the Envirothon. And the purpose of our being here today is to help you to prepare for that. And there's no better way to prepare for learning about soils than to getting your hands dirty and digging holes and looking at the soils and following a template that you'll find in your Envirothon participant manual. And in that manual, in the soil section, you're going to find a soil evaluation exercise. And that's what we're going to go through here today. We're going to go through that exercise, and we're going to cover several topics, including soil formation, soil horizonation, and then within each of those horizons, we're going to talk about various soil properties, including color, texture, structure, and consistence. We're going to describe those, or show you how to describe those. And then what's the big deal after that? So you make this document and you describe what you're finding in the field. But what's the practical application? Practical application is interpretations for land use and land management. Understanding the soils provides tremendous clues as to the behavior of the land. And therefore, if you understand that, then you can make better decisions about the land. So we'll go through some examples of how we can do some soil interpretations. So without further ado, we'll get right into this. What I've done here, we're in a woodland in western Massachusetts, and I have this mantra when it comes to talking about soils and learning about soils, and that is, yes, you have to look at the whole, but you also have to look at the whole. You have to look at the HOLE, but also the WHOLE. So the first thing to do is figure out where in the world are you in relation to what's around you. We're in an upland position. We're actually on the western edge of the Worcester Plateau. We're in a hilly area, and that should tell you something about the nature of the soils right away, because glacial depositions are of a particular kind in the upland, hilly parts of the state of Massachusetts, as the entire glaciated Northeast. So that can give you some clues as to what you can expect to find immediately. So I would expect to find soils that are fairly loamy in texture, meaning they have a lot of fine sand and medium sand and silt and maybe a little bit of clay. I would expect that we're going to have a very poorly sorted glacial deposit that is comprised of everything from small clay particles all the way up to boulder-sized rock fragments. And I expect that those rock fragments to be angular in shape, and that's because of the nature of the deposition in these upland positions. These upland positions are the most predominant situation in the state of Massachusetts. If you understand the state of Massachusetts, you know that most of it is hilly, and that's where the material that was carried by the glacial ice simply dropped out onto the surface of the land, and that's what we have here. So we can expect that before we even come out into the field and start to look at the HOLE. So to look at the HOLE certainly takes a little bit of work, and I understand in some situations for some Envirothon students, It also it could be a challenge, because if you're in an urban area, you might have to be creative as to finding places where the soil is relatively undisturbed and you can see an undisturbed soil profile. But in order to look at soils and understand soils and investigate soils, you have to dig holes, you have to get your hands dirty, and wear clothes that you don't care about. So we have this soil profile. We're in a road cut in a woodland. This is an old logging road. And this was fortuitous because it was relatively easy to cut back the road cut and expose the fresh soil profile. So here's our soil profile, and how did it get to be the way it is? Well, as I said before, there was glacial ice covering this entire area, and as it dumped out what it was carrying, it left behind what we refer to as the parent material of that from which the soil developed. So, and after the parent material is deposited, soil formation processes occur. Plants start to grow on the surface. They start to break down. They leave behind decomposed organic matter, which enables higher order plants to become established. There are various physical and chemical processes that occur over the course of time, and these layers start to form in the soil that we refer to as horizons. And you can imagine where that word came from, and you can see layers in this soil profile that are horizontal, and that's where the word comes from. So what sorts of horizons does an Envirothon team need to know about? Well, there are some basic kinds, and I'll go through them very quickly here. And if you go back and look at your manual, you're going to find all of these things described. But basically, we're talking about an O horizon, A horizon, B horizon, C, possibly E, and possibly R. And I'll go through those very quickly. An O horizon is organic material. It's a layer that is comprised predominantly of organic material. But what does predominantly mean? That's a good question. You're going to see that the organic material is going to have the predominant characteristics of a very greasy feeling. If you get a bunch of it in your hands and you get it good and wet and you squeeze it, it'll filter through your fingers like mashed potatoes. Whereas other horizons won't do that because they're predominantly mineral and they're going to hold together in your hand. The next major type of horizon that you should know about is the A horizon. This is a mineral layer that has an enrichment or an accumulation of organic material. And it's very typically on the surface or near the surface of the soil profile because that's where the plants are. And it's typically darker than the underlying material because of that accumulation of organic material. The organic material is what makes the soil darker, typically speaking. You're going to hear me say words like typically and generally and usually a lot because when it comes to soils, it seems like there's always an exception to the rule. So we soil scientists really enjoy those weasel words, typically, generally. We don't want to, really, it's hard to say things in absolutes because of those exceptions. So this soil profile is pretty typical of what you can expect to find in an upland position in Massachusetts. And you'll see that from about, this measure is in inches, by the way. You'll see that from about 0, or the surface, to about 20 inches, there's a very significant dark layer. That's the A horizon. Does this soil have an O horizon, which is what you would typically find on the surface? Envirothon students have a hard time with this. Don't feel badly. People who are experienced with this for years and years have a hard time sometimes deciding whether or not it's an O horizon or an A horizon. Does this soil have an O horizon? I scraped off a little bit of material, probably less than 1/4 of an inch, off the surface that is obviously predominantly organic material, just starting to decompose. That would be an O horizon. Not all horizons look like this because of various degrees of decomposition. Some horizons are so well decomposed that you can't identify individual fibers. But again, when you wet it and you squeeze it, it's going to feel very, very greasy, and it's not going to have any strength. It will squeeze through your fingers when wet. So we do have a thin O horizon on this soil profile, immediately underlain by a very thick A horizon. When I say very thick, this particular soil is unusual. Typically, you're not going to find an A horizon that's this thick. In this particular situation, when I look above me at the slope up behind me, I can see that there had been some disturbance, and there had been some sloughing that had occurred here when the soil was probably bare and it had been clear cut. Again, maybe some excavation of some sort to level off the hillside. There has been some erosional downwasting on this hillside, resulting in a particularly thick A horizon. Typically, you're not going, in a wooded situation, you're not going to find an A horizon that's much more than about 6 inches thick. But you can see that the A horizon is darker, significantly darker than the underlying material. So what's the underlying material? Typically, but not always, typically you'll find a layer that has undergone a weathering process. So a predominantly mineral layer that is not altered significantly by an enrichment of organic matter, but has undergone some soil forming processes, is referred to as a B horizon. It simply means a layer of alteration or a layer of weathering. And what sorts of weathering can have occurred? Things like an accumulation of clay material from the overlying layers, or aluminum or in iron that can accumulate in the B horizon from the underlying areas. So it can be a layer of what we refer to as illuviation, where materials moved into it. Very typically in our soils in Massachusetts, the weathering process is an oxidation process, where iron has oxidized from the inherent mineralogy of the soil and has coated individual soil particles, leaving behind a predominantly or reddish or yellowish brown, reddish brown color. And you can see this if you can get down deep enough to the material that's underlying the B horizon. And underlying the B horizon typically is the parent material of the soil, the relatively unweathered geologic material or geologic deposition. And in our case, in this upland position, that material is the glacial till that was deposited directly from the glacial ice. And the relatively unaltered parent material, with regard to color, is usually reflective of the bedrock from which that parent material is derived. It happens to be in this part of the world where we are right now that our bedrock is a granitic gneiss, which is a fairly light colored rock. It's grayish in color. So the underlying the material underneath the soil profile is reflective of that color, a grayer color. So in this particular soil profile, there are 4 major horizons, fairly well expressed. A thin O horizon underlain by an A horizon, which again is a mineral layer with an enrichment of organic material, underlain by a B horizon, that altered layer, underlain by the soil parent material. And when I say typically, there are exceptions to the rules. There can be dual parent materials. There can be, on floodplain situations, there can be buried surface layers, buried from recurring flooding events. So again, there are exceptions to the rules, but this is a pretty typical profile. I did mention that there are a couple other soil layers that we recognize are horizons. One is an E horizon, which is a layer of eluviation, meaning that material has exited from that layer, and that material is translocated below that layer into the B horizon. It's a very ashy looking layer. So typically you might see an O horizon underlain by this AE horizon underlain by a B horizon. They're not that well expressed throughout the state of Massachusetts. It would be unusual to come across it, but you might. And the other layer that we recognize is simply the bedrock. You may encounter scenarios where the soil profile is relatively shallow to bedrock, and if you were to designate that bedrock layer, you would do that simply with a capital R. So those are the horizons that you are likely to find in the state of Massachusetts. Just to reiterate, the O horizon, which is organic, the A horizon, a mineral layer with an accumulation of organic material, the B horizon, the weathered layer, and the C, which is the relatively unweathered parent material. Okay, so what? Well, now we're going to look at some various soil properties associated with each of one of these layers, and we'll do probably just one example of each. Soils have properties, a myriad of properties. They have chemical properties, physical properties, various sizes of rock fragments. They have various textures based on the percentages of sand, silt, and clay. And those properties are important for land use and interpretation. And so we'll start by talking about soil properties, and then we'll go into the interpretation of the soil for various land uses. When examining soils, it's helpful to have a few basic tools with you. It's good to have a spray bottle of water, because and you'll see why. We'll do an example of soil texture, but you have to have a water source. And also, if your profile is very dry, you'll find that if you wet it with a spray bottle, that a lot of the morphology is more distinct, and it's easier to pick it out. Some sort of a knife or a hand trowel will work to be able to pick at the soil and get samples out. A measuring tape so that you can document the thickness of each of the layers. Let's see what else. If you have a color book, it's useful, but it's not. This is a Munsell color book, and these are expensive, and it's not crucial to actually have one. I think what's more important is just understanding the contrast between horizons, the color contrast that is, and understand why there's a color contrast. And as a group, if you're with your Envirothon team and you're doing this exercise, if you don't have a Munsell color book, that's fine. I would suggest you just come to some consensus as to how you want to describe the color. Dark brown or yellowish brown or grayish or whatever, as long as you're somehow distinguishing one layer from the other. Well, we'll start with the A horizon. I'm going to grab a sample of this. And the first thing I'm going to note is, does the soil have structure? And as I gently put a little energy on this, I'm seeing that the soil is breaking up into individual aggregates. The propensity of the soil to form these aggregates results in what we refer to as soil structure. That's not to be confused with the clods that might form when a field is plowed. That's not the same thing. Those are clods that are being made as a result of physical manipulation. Soil structure is a naturally formed property, and it's an important property because if the structure is well developed, that has an effect on things like soil water and air infiltration, root infiltration, and it also increases the pore space within the soil and provides homes for the microbes that live in the soil. And the microbes in the soil are very, very important to the health of the soil, and it's functioning as a part of our ecosystem. So soils with good, well-expressed structure, that's an indication that you've got a functioning soil from the perspective of productivity, an environment for microbes, and an environment for plant growth. The next thing I would do is I would look at what we refer to as consistence. The consistence of the soil is simply its strength. It's the amount of pressure that is required to break up that soil aggregate. And in the case of this A horizon, it takes very, very little pressure to break that up. So I would describe this soil as friable. All of this is described in your manual, and you'll see that there are classes for consistence that range from very friable to extremely firm. The important thing is not necessarily getting the class exactly right, but getting a sense of how firm that soil is. Is it densely compacted? Is it going to allow roots and air and water to run through it or not? The next thing we're going to look at is the soil color. And we use the soil color book if you have one, but again, as I said before, it's not crucial. And you simply compare the soil color to a chip in the color book. And it's simple enough to do. Then you would document that color. And there's a method to do that. There's each one of these pages in the book has a predominant hue, which relates more or less to the color in the rainbow, in addition to the chroma of the color and the value of the color. The chroma is the strength of the color, and you can see that as you increase or increase in chroma from the bottom of the page up, you'll see that the color gets brighter, and the value increases from the left-hand part of the page to the right-hand part of the page, and you can see that that color is more distinctive. So then that's how you would document this. You would write down the hue, the value, and the chroma. And in this case, I determined that the color of this soil is a 10YR 3, 3. And that's how you would write it as a fraction, 3 over 3. YR refers to yellow-red. The 10 refers to the amount of yellow in it versus the amount of red. Again, it's not the most crucial thing. If you don't have a color book, that's okay. More importantly, than the actual color notation is recognizing that there is a difference in color and why. That's the more important thing. And then lastly, we're going to determine what the texture of the soil is. How do we do that? Get about a golf ball size sample of soil. Remove anything that's above sand size. And sand size in the USDA textural system is anything greater than 2 millimeters, so not very big. And sometimes that's difficult to do, to remove everything that's just bigger than 2 millimeters, but you do the best you can. And in this sample, I'm not really finding much of that. Then you want to wet your sample to about the consistence of putty. And that's what I have here. And then you'll refer to a soil texture flow chart. We're going to determine the texture of the soil. And you would do this for each layer as you describe the soil at each horizon. And again, you would get about a golf ball size sample, remove the fragments greater than sand size, which is 2 millimeters, and then use this texture field flow chart. It's basically a yes/no dichotomous key. So it's going to ask you to recognize a property, and you'll simply say yes or no with regard to to what the soil property is, and that will lead you down to the next step of the flow chart. And one of the first questions is does the soil form a ball? Well, in this case, obviously, yes, it does. And then, will the ball hold together? And this certainly does. If it doesn't hold together, what is that telling us? It's telling us that there's very little clay and very little silt. And I should back up a little bit here. Soil texture is the term that refers to the proportions of sand, silt, and clay in the soil. And as you all know, sand feels gritty. Beach sand, you're familiar with that perhaps, or sand that's laid on a road in the wintertime. We all know what sand is. The next smallest size particle is the silt ranged particles. Silt particles feel very, very, very smooth. Silt is often compared to the feel of talcum powder or baking flour. So if you go into the kitchen and you grab a handful of baking flour and you rub it between your finger and your thumb, that gives you a sense of what silt feels like. It's very, very smooth. It's not gritty. And clay particles are unique in that they have an adherence quality. These are the smallest soil particles that we recognize, and they have both a chemical and a physical bond to one another. And so they're very, very sticky, and they're very, very plastic. They hold together really, really well. So a soil that doesn't have very much clay and doesn't have very much silt and is predominantly sand is not going to hold together. So we already know that this is not a sand or a loamy sand based on the flow chart. The next thing you're going to do is see if the soil forms a ribbon. What does that mean? Well, you hold the soil in your hand and you push the soil from below, from your sample, and you essentially extrude it over your forefinger, and you note at what length that sample breaks off from the force of gravity. And if that sample breaks off and it's less than 2.5 centimeters or an inch, that's going to put you in another direction in the flow chart. If it's greater than an inch, that'll put you in another direction in the flow chart. And without going through the entire thing, because this is in your manual, you'll see what the process is. Based on whether or not you can get a ribbon and what the length of that ribbon is going to help you determine your soil texture class. And in this case, because it has a ribbon that's less than 2.5 inches, that's going to limit our choices to, let's see, we've got, if it's less than an inch, our choices are sandy loam, loam, or silt loam. So, how do we determine whether it's a sandy loam, a loam, or a silt loam? We take another piece of the sample, a very small piece, we put it in the palm of our hand, we wet it excessively, and then rub it on the palm of your hand, and then you ask yourself these questions. Does it feel very gritty? Does it feel very smooth? Or does it not feel smooth or gritty if neither one predominates? And that gets somewhat subjective, but that's what the flow chart is going to prescribe that you're going to do. To me, this feels pretty gritty, so I would come to the conclusion that this is a sandy loam. If it felt very smooth, it would be a silt loam. If it didn't feel like one or the other was predominant, then I would go with a loam texture. And by the way, most of the soils in the state of Massachusetts are going to have less than about 10% clay. So very few of our soils are going to be in the clayey texture ranges. So just another tip with regard to forming the ribbon, you don't want your ribbon to be more than about 1/8 of an inch in thickness when you're doing this test. And again, you're measuring the ribbon that is held by the force of gravity, so that when that breaks off, that's what you're going to measure, as opposed to sort of letting it sit on your finger. You want to measure, again, that which is not held with gravity. The next thing we're going to talk about is whether or not the soil has what we refer to as redoxomorphic features. That's just a very fancy word that is used to more or less describe the bathtub ring in the soil profile that is left by a fluctuating seasonal high water table. In a nutshell, what happens is if the soil has a water table in it, and the water table rises up to a point in the springtime, which is typically the wettest time of the year in our part of the world, what can happen is that the iron in the soil, which is the predominant coloring agent in the mineral part of the soil, can be either oxidized or reduced. Under anaerobic conditions, the iron becomes reduced, and it no longer adheres to the soil particle due to a change in electrical charge, and it leaves the soil particle and leaves behind what you see, which is the inherent mineral color of the soil, as opposed to oxidized iron, which adheres to individual soil particles and coats the individual soil particles, which is the predominant color that you see. And in this particular soil profile, it's that iron oxides that are the predominant color of the B horizon. The oxidation process has resulted in the oxidation of iron and the coating of the iron over individual soil particles, individual silt particles, individual sand particles, producing that predominantly yellowish brown color. So what you're looking for in the soil profile, and this is very important for the perspective of land use, is there a sign, a morphological sign in the soil as a result of that seasonal high water table? And I do see that in this soil. I can see variable colors in the soil, gray colors, reddish orange colors. They're the direct result of this reduction and oxidation process. So where you encounter these features in the soil, that is telling you what the depth from the surface to the seasonal high water table is. So it's important to recognize where you see these features. Again, they're referred to as redoxomorphic features. And if you think about the name, you can hear reduction and oxidation abbreviated in the name, and that's where it comes from. It's the oxidation and reduction of elements, predominantly iron, but others as well, manganese, etc. But it's predominantly iron is the one you're going to be looking for. And in this soil profile, I'm seeing redoxomorphic features coming in at a depth of about 28 inches. So that's telling me that in the wettest time of the year, this profile is saturated at that depth. So that's an important thing. We assign what we refer to as a drainage class to a specific soil based on the depth to the seasonal high water table, as indicated by the redoxomorphic features, and the ability of the soil to have water removed from it. So, for example, soil that is excessively drained is one that's fairly high on the landscape, far away from the groundwater, that is highly permeable, a very sandy soil. Water is removed from it very quickly, and there's no water table within that soil profile. The other end of the extreme is a very poorly drained soil, where the water table cannot drain away from that soil or from that landscape segment readily, and the water stays at or near the soil surface for a significant period of time throughout the course of the year. So we've got these different drainage classes, and again, if you look in your manual, there's sort of a guide for determining what the drainage class is based on the texture of the soil and the depths of the seasonal high water table as you recognize it by seeing the redoxomorphic features. this particular soil would come out to be moderately well to a well-drained soil. So now we've described the soil, we've recognized the horizons, we've recognized different soil properties. So what's the significance of that? Well, we could ask ourselves some questions. I mean, based on the soil texture, how well does this soil provide water to growing plants? Well, it's a sandy loam, so it's got a bunch of silt in it, it's got some fine sand in it, it has a pretty good available water holding capacity. That's the sort of thing that we can derive from having evaluated soil properties. How about, we'll think of some common uses for soils in Massachusetts. Farmland. How is this soil going to be for farmland? Well, in of itself, it's not too bad. You can see some rock fragments in the upper part. That will inhibit conventional farming practices, perhaps. So that's a limitation of the soil for agriculture. And yet, it has pretty good water holding capacity. But the biggest limitation at this particular site is, if you're looking up behind me, the soil is on a very steep slope. So that would be the biggest limitation for agriculture. If this soil were on a level area, it would be well suited for agriculture. Okay, how about another common use of land in Massachusetts? Of course, housing with full basements. What would the issues be here that are soils related? You've got a seasonal high water table within about 28 inches. If you put a basement in the ground, then you have to account for that. You have to be able to put in some drainage around the basement so you're draining water away, and that drainage has to be effective enough to not result in water coming into your basement. The slope is also a bit of a limitation for a house, because you've got to get around that steep slope scenario. Another typical land use in Massachusetts are on-site septic disposal systems. It's very common land use, and there are folks whose job it is to evaluate the soil for the suitability for septic systems. And they're looking for impermeable layers, and they're looking for the redoxomorphic features. This particular soil, again, the slope is an issue. The depth of seasonal high water table is an issue. And there's one other issue that I probably should have talked about earlier, is that the parent material of this soil, remember we talked about the consistence, it's very difficult to dig in this material. It's a very firm, dense material. It's a type of till that we refer to as lodgement till or subglacial till. So when you try to dig in it, you know immediately it's highly compacted. It has a very firm consistence. It's restrictive to the downward flow of water. It's restrictive to root growth. So in this particular situation, it is that dense layer that is causing the perching of water that is resulting in the redoxomorphic features above it. So again, it's very important to get your hands dirty and to examine the soil, not only from just observing its morphology, but to actually get your hands dirty, feel the soil, dig in it. You can learn an awful lot about the soil by digging a hole in it. And again, that's a very compact layer. You can hear the spade thud when I dig into it. And if I pull out a piece, it sort of pops when I put pressure on it, and it'll resist my pressure until it can't anymore, and the thing will just sort of pop. Indicative of a dense or extremely firm consistence. So we've described this soil. We know something more about its formation and how it formed with that dense layer and the loamy permeable material above it and the horizonation that's been formed. And we have an idea of, or a perception of, what the soil is good for and what it's not necessarily suited for. And one of the big takeaways with this particular soil is recognizing that one of the biggest limiting factors is that dense layer. And you're not going to see that unless you dig a hole and you experience what it's like to dig in this thing. We talked about how this soil, we would designate it as being a moderately well-drained soil. It's fairly aerated in the upper part, fairly bright colors due to the oxidation of iron. And as you go deeper into the profile, we do see these redoxomorphic features that are indicative of a fluctuating water table. We're seeing pockets of grayer colors where the iron's been reduced and removed from the soil particles, and pockets of reddish orange colors or reddish brown colors where the soil has become re-aerated as the water table dropped and that iron precipitated out. So you see what we refer to as a modeling color. And by contrast, just wanted to show you, not 200 feet from here at the base of this slope, there's a flatter area where water from this slope is moving down along that dense lodgement till, and it ends up being moved to the slope below us on this flatter area. And as a result, you have a soil that experiences saturation close to the surface throughout much of the year. And you may be able to see that the surface layer, just by way of comparison, the surface layer, or the A horizon, is significantly darker because it has more organic matter. And that's because these soils are saturated for significant periods of the year. And under saturated conditions, the organic matter does not break down very readily. It tends to build up. And directly underneath the A horizon, you don't see the bright B horizon that you see in this profile. You see a predominantly gray layer immediately under the A horizon. That's the result of predominantly anaerobic conditions because the soil is saturated for long periods of time, and the iron doesn't precipitate out, it doesn't get oxidized, it goes into solution in the soil, in the water environment. So here's a difference between a moderately well-drained soil and a poorly drained soil. We're in a low-lying position in the Connecticut River Valley, surrounded by hills. And when I look around, I see that behind me there's a broad, level plain, and before me a gently sloping plain, again surrounded by hills. And this low-lying area is very distinctive in its position in the landscape and as a separate landform. And when we come and we look at the soil, we see there's very well-sorted sands, predominantly sands with some gravels. Between the position of the landscape and what we see in the profile, we can conclude that this material was deposited by glacial meltwater. And that parent material is referred to as glaciofluvial or glacial outwash. The two words mean the same thing. And the resulting profile is much different than the one we looked at earlier. Sandy material versus loamy material, rounded rock fragments versus angular rock fragments, and a very highly permeable material. Water and air will move through this material quite readily. We're also fairly high on the landscape, and so I would not expect to see redoxomorphic features or any indication of morphology that would be indicative of a seasonal high water table. This is a high, dry, excessively drained, highly permeable, well-aerated soil. When we look at the soil profile itself, I immediately see two distinctive horizons, and I'd be hard-pressed to pick out more than two. This is a little bit unusual in that I'm not seeing a distinctive B horizon. As we talked about before, there are major soil horizon types that we equate to soil development, and the A horizon is that darker layer with the accumulation of organic material. The B horizon is an altered layer, and the C horizon or C layer is the relatively unweathered parent material. In this particular horizon, I'm not seeing a very distinctive B horizon at all. So what we have here, arguably, is an AC profile, an A horizon, the mineral layer with an accumulation of organic, and the C horizon or C layer. If you use your imagination and you squint sideways, you might be able to see a little bit more brightness in the depth from about 12 inches to about 16 inches, but it's not very continuous throughout the soil profile. So I'd be hard pressed to describe a distinctive B horizon here. With regard to texture, we can look at the surface layer, make a determination on texture. Again, we want to try to remove the fragments that are larger than sand size. It forms a ball, and the ball holds together, which puts us finer than a sand or a loamy sand. I'm guessing this is very gritty feeling, and it may be the organic component that's causing this to hold together. This is a pretty sandy soil, although it does have some silt in it. So let's talk about how this soil profile or this soil interprets with regard to suitability for land use. Again, we'll use the same examples that we used before. Typical land uses in Massachusetts, one being agriculture. What do folks think? How suitable would this soil be for agriculture? It being sandy, with a high volume of macropores, it's not going to hold a lot of water. So there's an issue there with regard to available water holding capacity in the soil. Suitability for agricultural use. The soil it's essentially droughty, has a low water holding capacity. The A horizon has a fairly good accumulation of organic material, so it has a decent available water holding capacity, but just below that, it drops off very quickly. And you might be able to see in the soil profile itself, you'll see how the root mat is contained, or it's predominant in the A horizon. And there are root fibers that continue down through the C material, but they are not as dense. And the reason for that is available water holding capacity, nutrient cycling that occurs as a result of that organic accumulation in the A horizon. This soil extends behind us to a fairly broad plain, and because it's level and it has enough water holding capacity to be not too limiting, the soil is fairly suitable for agriculture, although irrigation may be necessary for maximum crop growth. Dwelling with a basement, any restrictions for that? The soil is high on the landscape. It's not subject to a seasonal high water table. It's actually pretty well suited for a house with a basement. This may be one of the situations which is the exception rather than the rule in the state of Massachusetts, where one does not have to worry about water in a basement. However, if you're going to build a house, you also have to have a septic system. What would the limitation be for a septic system? Because you are putting effluent into a leach field and you'd be putting it into this highly permeable material, there may be an issue with that effluent not being properly treated before it moves down through the down through the soil profile to eventually encounter the groundwater aquifer. So a poor filter would be a limitation of this soil for on-site sewage disposal. So we've seen a contrast of two very different soils and a contrast in their suitability and limitations for land use, how they formed. Their profiles are very different. The material that comprises the soils are very different. And the point, I think, it points to the fact that because So many different factors go into soil development and soil morphology that it results in a great range and variabilities in soils. And understanding that range and the properties associated gives us a great deal of insight with regard to land use and management and making wise land use decisions. One other thing that's sort of interesting at this site, I think, is that when you look at the underlying glacial outwash deposits, it's fairly dark in color. And that's in contrast to most minerals, most mineral colors. You'll see this is actually looks like it's quartz, and that's a pretty typical bedrock type color. But in this particular deposition, there's a mix of this darker material. And that dark material is referred to as Phillipe. And you can see that it makes good skipping stones. It tends to be flat, and when it's worked by glacial meltwater, not only is it flat, but it's fairly well rounded. So it's sort of unusual. And where soils are developed in this darker mineralogy, there can be issues with interpreting the morphologies that result from saturation. And one needs to be careful about that, because we always talk about soils that are very gray. Soils that have a very gray color being associated with saturated conditions, because the iron, which normally gives a soil a bright color, is not there to coat the individual soil particles and give it that brighter color. Under reduced saturated conditions, we lose that iron coating, and what's left behind are these darker gray or these grayer colors. And that's something to be aware of when you're in an area where you have mineralogy that's dark. That can be open to misinterpretation. So that's something to be aware of if you do get into the environment, into an area where you have this dark material. You might want to kind of check that out ahead of time. And the site of the environment is always provided to people, and you can learn about that site ahead of time, and there's nothing wrong with that. You can go to the Web Soil Survey, and if you Google Web Soil Survey, that will be the first hit on the web that will pop up, and you can use that to identify an area of interest, and you can read about the soils and their parent materials and the lithology from which the parent materials developed, and learn something about what to expect before you get involved with trying to actually tackle the environment. And that's a good exercise for you to do for preparation, or in preparation of the environment. Check out an area of interest, check out where you live, check out where your school is, and learn about what the soils are like. And before you come out to do this soil evaluation exercise that's in your manual, check out the soil survey first. See what the soil survey has mapped in that area that you're going to go investigate. It will give you an idea of what to expect and help to guide you when you go through this exercise. So I hope that you received a good overview of how to better understand soils and their properties and apply it to a practical purpose.